All right, this is Unit 3, Lesson 3, Polynomial Identities. So during this lesson, how can you use polynomial identities to rewrite expressions efficiently? And at the end of this lesson, we'll be able to prove and use polynomial identities. All right, so the main concept of polynomial identities. So it's a mathematical statement that equates two polynomial expressions is an identity if one side can be transformed into the other side using mathematical operations. So these polynomial identities are helpful tools used to multiply and factor polynomials. So we have the difference of squares, which is a squared minus b squared, which equals a plus b times a minus b. So for example, 25x squared minus 36y squared. 25 and 36 are both squares, so I can take the square root of them. They're perfect squares. X squared is also a perfect square, and so is y squared. So I take 5x, which is if I took the square root of 25x squared, so 5x and 5x, and then the square root of 36y squared is 6y, so 6y and 6y. So, and I just have a plus in front of one and a minus in front of the other. Now, if I were to go through and FOIL this, I would actually come out with 25x squared minus 36y squared. So that was just a quick, this one's really helpful to kind of know just because it's very quick and easy to be able to factor something that's a difference of squares. The square of a sum. So a plus b squared is a squared plus 2 times ab plus b squared. So if I have 3x plus 4y squared, I take 3x squared plus 2 times 3x times 4y plus 4y squared. So 3x squared is 9x squared. 2 times 3 times 4 is 24. X times y is xy. Plus 4y squared is 16y squared. Difference of cubes. So that's a cubed minus b cubed equals a minus b times the quantity a squared plus ab plus b squared. So 2m cubed minus 27, both of these are perfect cube roots. The cube root of 8m cubed is 2m, and the cube root of 27 is 3. So I substitute those values in. So I have 2m minus 3 times 2m squared plus 2m times 3 plus 3 squared. So 2m minus 3 times 4m squared plus 6m plus 9. And then the sum of cubes. So a cubed plus b cubed is a plus b times a squared minus ab plus b squared. So basically it's the same formula. I'm just switching the plus and the minus signs for the first two. So g cubed and 64h cubed are both cube roots. Cube root of g cubed is g. Cube root of 64h cubed is 4h. So g plus 4h times g squared minus g times 4h plus 4h squared. So that gives me g plus 4h times quantity g squared minus 4gh plus 16h squared. All right, so in example number 1, I want to prove a polynomial identity. So how can you prove the sum of cubes identity? So I have a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. So in order to prove an identity, I start with the expression on one side of the equation and use properties of operations on polynomials to transform it into the expression on the other side. So I basically want to take this and I want to change it so it looks like this. So I have a plus b times a squared minus ab plus b squared. Well, I can say that this is multiplying a times this trinomial plus b times this trinomial. That's using the distributive property. When I do that, I get a cubed minus a squared b plus ab squared plus a squared b minus ab squared plus b cubed. That's the distributive property. I'm going to go ahead and group all my like terms together. So I have a negative a squared b plus a squared b, and then plus ab squared minus ab squared. When I simplify these, they equal 0, so I'm left with a cubed plus b cubed. So a plus b times a squared minus ab plus b squared gives me a cubed plus b cubed. All right, so I want to prove the difference of cubes identity. So again, the difference of cubes. So the difference of cubes states a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. So I want to prove this. So I want to take this a minus b times a squared plus ab plus b squared, and I want to see if I can get it to equal the a cubed minus b cubed. Well, I'm going to go ahead and use the distributive property. So when I do that, so I get a times a squared plus ab plus b squared minus b times a squared plus ab plus b squared. Now I go ahead and distribute. So a times a squared is a cubed. A times ab is a squared b. And then a times b squared is ab squared. And then I have minus b times a squared is a squared b. Negative b times ab is negative ab squared. And then negative b times b squared is negative b cubed or minus b cubed. Now I'm going to group my like terms together. I had a squared b minus a squared b, and then plus ab squared minus ab squared minus b cubed. Okay, so when I simplify this, I get a cubed minus b cubed. All right, example 2, use polynomial identities to multiply. How can you use polynomials identities to multiply expressions? So I have 2x squared plus y cubed raised to the second power. So the sum is a binomial, and the entire sum is being raised to the second power. So I can use the square of a sum identity to find the product. So really, this is like saying 2x squared plus y cubed times 2x squared plus y cubed. Okay. So this is what I'm using. So a plus b squared equals a squared plus 2ab plus b squared. Well, a is 2x squared, b is y cubed. So I have 2x squared squared plus 2 times 2x squared y cubed plus y cubed squared. Okay, so that gives me 2x squared squared is 4x to the fourth power. So remember, we distribute this top 2 to the 2 inside, both 2's inside. And then I have 2 times 2, which is 4, times 1, which still gives me 4, x squared y cubed plus y to the third raised to the second power is y to the sixth. So that's an exponential power to a power rule. So you multiply the exponents. So 2x squared plus y cubed squared equals 4x to the fourth plus 4x squared y cubed plus y to the sixth. All right, how can you use polynomial identities to multiply expressions? So 41 times 39, I can rewrite the expression in terms of a and b. So 41 times 39 equals a plus b times a minus b. So 41 equals 40 plus 1, and 39 equals 40 minus 1. This is the difference of squares identity. So I take 40 squared minus 1 squared, so 1600 minus 1 gives me 1599. All right, use polynomial identities to multiply the expressions. So I have 3x squared plus 5y cubed times 3x squared minus 5y cubed. So this is going to be a difference. Okay, so this is actually a difference of squares. So a squared minus b squared equals a plus b times a minus b. Okay. So when I do this, I get the first number squared minus the second number squared. So 3x squared minus y cubed. Okay, so this gives me 3 squared is 9. 2 times 2 is 4. 5 squared is 25, and then 3 times 2 is 6. So 9x to the fourth minus 25y to the 6th. And then I have 12 plus 15 squared. Okay, so that's the square of a sum. So that's square of a sum. So that's a square of a sum. So that's a plus b squared equals a squared plus 2ab plus b squared. Okay. So I'm going to take a equals 12, b equals 15. So I have 12 squared plus 2 times 12 times 15 plus 15 squared. 12 squared is 144. Two times 12 times 15 is 360. And then 15 squared is 225. Oops. 144 plus 360 plus 225. When I add all of those together, I get 729. This, of course, is not the only way that you can solve 12 plus 15 squared. You can add them together and then square that number. You'll still get 729. All right, example number 3, use polynomial identities to factor and simplify. So how can you use polynomial identities to factor polynomials and simplify numerical expressions? So I have 9m to the 4th minus 25n to the 6th. So these are both perfect squares. The square term includes an even exponent, not necessarily an exponent that is a perfect square. So 9m to the 4th equals 3m squared squared, and 25n to the 6th equals 5n cubed squared. So I use the difference of squares identity, a squared minus b squared equals a plus b times a minus b. So I get 3m squared squared minus 5n cubed squared equals 3m squared plus 5n cubed times 3m squared minus 5n cubed. So that's my final answer. How can you use polynomial identities to factor polynomials and simplify numerical expressions? So x cubed and 216 are both perfect cubes. X cubed is x raised to the 3rd power, and 216 is 6 raised to the 3rd power. So I can use the difference of cubes identity, a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Well, this gives me x minus 6 times x squared plus 6x plus 36. How can you use polynomial identities to factor polynomials and simplify numerical expressions? So I have 11 cubed plus 5 cubed. So this is the sum of cubes. I have a cubed plus b cubed, which is a plus b times a squared minus ab plus b squared. A is 11, b is 5. So I have 11 plus 5 times 11 squared minus 11 times 5 plus 5 squared. Okay. So I get 16 times 121 minus 55 plus 25, which gives me 16 times 91, which gives me 1,456. So 11 cubed plus 5 cubed is 1,456. And you can also take 11 cubed plus 5 cubed, and you will get the same answer. All right, so let's try it out. Use polynomial identities to factor each polynomial. So I have 8 to the m power minus 9n to the 10th power. So both of these are square roots. So if I have m squared to the 4th power minus 3n squared to the 5th power. Okay, this is the difference of two squares. So I have a squared minus b squared equals a plus b times a minus b. So I'm going to take actually, I'm going to go the other way. You should be 10 to the 4th 3n to the 5th squared. Okay, so A equals m to the 4th, and B equals 3n to the 5th. So I have m to the 4th plus 3n to the 5th times m to the 4th minus 3n to the 5th. For letter B, I have 27x to the 9th minus 343y to the 6th power. So these are both cube roots. 27, the cube root of 27 is 3. Okay, and the cube root of 343 is 7. Okay, so 27x to the 9th equals 3x cubed raised to the 3rd power. And then 343y to the 6th equals 7y squared cubed. Okay, so this is a difference of cubes. Okay, so difference of cubes is going to give me a minus b equals a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Okay, and we said a equals 3x cubed and b equals 7y squared. So when I do this, I get 3x cubed minus 7y squared times 3x squared squared plus 3x cubed times 7y squared. This should be a cubed. Plus 7y squared squared. Okay, so when I do that, I get 3x cubed minus 7y squared. 3 squared is 9. 9x, and 3 times 2 is 6. Plus 3 times 7 is 21, x cubed y squared. Plus 7 squared is 49, y squared squared is y to the 4th. We get 3x cubed minus 7y squared times 9x to the 6th plus 21x cubed y squared plus 49y to the 4th. All right, and then I have 12 cubed plus 2 cubed. Well, this is the sum of cubes. So we said the sum of cubes states a cubed plus b cubed equals a plus b times a squared minus ab plus b squared. Well, a equals 12, b equals 2. So I have 12 plus 2 times 12 squared minus 12 times 2 plus 2 squared. 12 plus 2 is 14. 12 squared is 144 minus 24 plus 4. 14 times 144 minus 24 plus 4 is 124. And then multiply that by 14 gives me 1736. 1,736. All right, example number 4, expand a power of a binomial. So how is x plus y to the nth obtained from x plus y n minus 1? What are x plus y cubed and x plus y to the 4th?
How is x plus y to the power of n obtained from x plus y to the power of n minus 1? Look at an example. Part A. What are x plus y cubed and x plus y to the power of 4? X plus y cubed is x plus y times x plus y squared. Squaring x plus y gives x squared plus 2xy plus y squared. To multiply x plus y by the quadratic, you need to multiply each term of the quadratic by x plus y. First, multiply x squared by x and then by y. Then do the same for 2xy and y squared. Combine like terms to find the simplified polynomial. This simplified polynomial is x plus y cubed. To find x plus y to the power of 4, multiply x plus y by each term of the cubic expression. Then combine like terms to find the new simplified polynomial. This simplified polynomial is x plus y to the power of 4. When the calculations are simplified, you can start to see a pattern. The coefficients of x plus y to the power of n are produced by adding the coefficients of x plus y to the power of n minus 1. This produces an array called Pascal's triangle. Pascal's triangle is a triangular pattern of numbers. In this pattern, each number is the sum of the two numbers diagonally above it. For example, this 6 is the sum of the two 3's diagonally above it. If there is not a second number diagonally above in the triangle, think of the missing number as 0. So this 1 is the sum of the 1 and a hidden 0.
All right, so how is x plus y to the nth obtained from x plus y to the n minus 1? So I can use Pascal's triangle to expand x plus y to the 5th. So I add pairs of coefficients from row 4 to complete row 5. So row 4 was 1, 4, 6, 4, 1. So remember, I have 1 on the outside, then 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5, and then 1 on the outside. I can then write the expansion, use the coefficients from row 5 with powers of x starting at 5 and decreasing to 0, and with powers of y starting at 0 and increasing to 5. So for example, I have 1 x to the 5th plus 5 x to the 4th y plus 10 x cubed y squared plus 10 x squared y cubed plus 5 xy to the 4th plus 1 y to the 5th. The sum of the exponents in each term is equal to the exponent on the original binomial. 4 plus 1 is 5, 3 plus 2 is 5, 2 plus 3 is 5, 4 plus 1 is 5, and 5. All right, so use Pascal's triangle to expand x plus y to the 6th power. So the triangle from above was 1, 5, 10, 10, 5, 1. Okay. So that means the next row is going to be 1 plus 5, which is 6, 5 plus 10, which is 15, 10 plus 10, which is 20, 10 plus 5, which is 15, 5 plus 4, which is 6, and then 1 on the outside. Okay, so this is my new row. That's the 6th row. Okay. So then I take 1 times x to the 6th plus 6 x to the 5th y plus 15 x to the 4th y squared plus 20 x cubed y cubed plus 15 x squared y to the 4th plus 6 x y to the 5th plus 1 y to the 6th. So x to the 6th plus 6x to the 5th. Okay, so you see how the exponents above start at 6 and they decrease for the x, but they increase for the y values. And I use the numbers from Pascal's triangle in order to get this polynomial. All right, so the concept of the binomial theorem states that for every positive integer n, a plus b to the nth equals c naught a to the nth plus c1 a to the n minus 1b plus c sub 2 a to the n minus 2 b squared plus blah, 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 all the way to c n minus 1 a b n minus 1 plus c sub n b to the nth. So the coefficients c naught 1, c sub 1, c sub 2, c sub n minus 1, c sub n are the numbers in row n of Pascal's triangle. So those are the 1, 1, 6, those numbers that we just dealt with. So like the 1, 5, 10, 10, 5, 1, the 1, 6, 15, 20, 15, 6, 1, those numbers, okay? Notice that the powers of A are decreasing while the powers of B are increasing, and that the sum of the powers of A and B in each term is always n. All right, so example 5, apply the binomial theorem. So I'm going to use the binomial theorem to expand the expression. I have find x minus 3 to the 4th. Okay, so the binomial theorem to write the expansion when n equals 4 is c naught a to the 4th plus c sub 1 a cubed b plus c sub 2 a squared b squared plus c sub 3 a b cubed plus c sub 4 b to the 4th. So I use the 4th row of Pascal's triangle, 1, 4, 6, 4, 1. I substituted my numbers. Then I make sure that my exponents are correct. Again, A starts at 4 and goes backwards. B starts at 0 and goes forwards. So identify A and B. So A equals x and B equals negative 3. Remember x, negative 3. So then I substitute in my values for x and negative 3, and then I simplify. So x to the 4th plus 4x cubed times negative 3 plus 6x squared times negative 3 squared plus 4x times negative 3 cubed plus negative 3 to the 4th. So I get x to the 4th minus 12x cubed plus 54x squared minus 108x plus 81. So x minus 3 to the 4th equals x to the 4th minus 12x cubed plus 54x squared minus 108x plus 81. Okay. So use the binomial theorem to expand the expression s squared plus 3 to the 5th. So the expansion of a plus b to the 5th is this. So a is s squared and b is 3. And then I substitute in for my values of a and b, which I get s to the 10th plus 15s to the 8th plus 90s to the 6th plus 270s to the 4th plus 405s squared plus 243. So s squared plus 3 to the 5th gives me this. All right, so I want to use the binomial theorem to expand each expression x minus 1 to the 7th power. All right, let me go ahead and pull up Pascal's triangle real fast. Okay. So here's my Pascal's triangle. I'm going to look at row 7, which is 1, 7, 21, 35, 35, 21, 7, 1. So I have 1, 7, 21, 35, 35. 1, 7, 21, 35, 35, 21, 7, 1. That's Pascal's triangle for this. So I had x to the, so a to the 7th plus 7a to the 6th b plus 21a to the 5th b squared plus 35a to the 4th b cubed plus 35a cubed b to the 4th plus 21 a squared b to the 5th plus 7ab to the 6th plus b to the 7th power. A equals x and b equals 1. B equals -1. Okay, and then I substitute in, so I have x to the 7th plus 7 times x to the 6th times -1 plus 21 x to the 5th times -1 squared plus 35x to the 4th times -1 cubed plus 35x cubed times -1 to the 4th plus 21x squared -1 to the 5th plus 7x -1 to the 6th plus -1 to the 7th. Okay. When I do that, I get x to the 7th plus minus 7x to the 6th plus 21x to the 5th minus 35x to the 4th plus 35x cubed minus 21x squared plus 7x minus 1. So again, this really is just kind of a process of take the time to actually sit down and work everything out. Okay? So it's not difficult, it's just time, it can be time consuming. All right, so I have for letter B, 2c plus d raised to the 6th power. So again, I'm going to go back to my Pascal's triangle. I have 1, 6, 15, 20, 15, 6, 1. 6th row. 1, 6, 15, 20, 15, 6, 1. Okay, so that's a to the 6th plus 6a to the 5th b plus 15a to the 4th b squared plus 20a cubed b cubed plus 15a squared b to the 4th plus 6ab to the 5th plus b to the 6th power. A equals 2c and b equals b. So I have 2c to the 6th plus 6 times 2c to the 5th times d plus 15 2c to the 4th d squared plus 20 2c cubed b cubed plus 15 2c squared e to the 4th plus 6 times 2c d to the 5th plus d to the 6th. Okay, when I multiply this through, 2 to the 6th is 64, so I have 64c to the 6th plus 2 times 6 is 12, so 12c to the, I have to, 2 to the 5th is 32 times 6, which is 192 c to the 5th d, plus 2 to the 4th is 16 times 15, which is 240 c to the 4th d squared, plus 2 cubed is 8 times 20 is 160 c cubed d cubed, plus 2 squared is 4 times 15 is 60 c squared d to the 4th, plus 6 times 2 is 12 c d to the 5th plus d to the 6th. All right, so concept summary. Overall, you have polynomial identities, which are special polynomial identities, can be used to multiply and factor polynomials. Difference of squares, square of a sum, difference of cubes, and sum of cubes. I would recommend that you memorize these. Okay, they will be very helpful for you. Binomial expansion. So the binomial expansion of a plus b to the nth has the following properties. The expansion contains n plus 1 terms. The coefficient of each term are numbers from the nth row of Pascal's triangle. The exponent of a is n in the first term and decreases by 1 in each successive term. The exponent of b is 0 in the first term and increases by 1 in each successive term. The sum of the exponents in any term is n. Okay, so I'd work on Pascal's triangle, at least understanding how you get Pascal's triangle. You won't always have it available to you, so knowing that the sum of the two diagonals above is what gives you each of these numbers, that will be very helpful for you to know if you don't have access to Pascal's triangle. All right, and that is the end of Unit 3, Lesson 3.